This is the Innova Engineering online training for short collar correction and the magnetic interference calculator. This video assumes that the viewer has some background knowledge of short collar correction and dual string magnetic interference. In this video, we're just going to be running through how to input the data into Innova Engineering and run the calculation. Before we start, I'm going to go over some of the other sources of information that we have available, and these are all accessed through the Help menu. So first we have Help, which opens up the manual. For this training video, the most relevant sections are going to be in the Menus section, in Options and the Options menu. There's some information on the raw survey QC limits. In the Calculate menu, this is where you can access the page for the well-path magnetic interference calculator. In the dual string section, the dual string and component grid page is relevant to us. And then in the survey section, pretty much this whole section is going to be relevant to us for short collar correction. But the most important sections for this video are the appendices at the bottom. So we've got Appendix C. This is a reference for your inclination and azimuth limits for short collar correction. And then in Appendix D, we have the pole strengths for our components based on their size and type. And it's these pole strengths that the magnetic interference calculator uses to estimate the effect of the steel components on the directional sensor. Next, we have online documentation. This will open up the documentation section of our website. And this contains a number of quick start guides. And under Innova Engineering, we have a QE/QC short collar correction and multi-station analysis guide. It also contains the manuals, so you can access the Innova Engineering manual online through this page. And we've got some video guides, so we've got some quick how-to video clips, and under Innova Engineering there is one for survey correction. Then we have Innova Online Trading, and this contains all of the online training videos, including this one, under the Innova Engineering section. We also have online videos, and that just opens up the website again, but it goes straight to the online training videos. The Open Documentation folder. This opens up a local folder in your Innova Engineering install directory. And this just contains local copies of all the quick start guides and the manual, so you can see the QA/QC short collar correction and multi-station analysis quick start guide is here. If you go to Open Install folder, this will open up your Innova Engineering install directory, and inside it we have an example projects folder. So this contains some projects that already has data entered into them. And we got a specific short collar correction example project, but for the magnetic interference calculator you can use any one of these as long as it has a BHA entered into it. We're going to run through short collar correction first because in terms of inputs it's the simplest. In short collar correction, the only input tab that you need to worry about is the surveys tab. You don't need to enter any data into the dual string tab, the engineering parameters tab, or any of the others. Before we start entering data, I'm going to give my project a name. And then I'm going to save it somewhere on my computer. So I'll go to File and Save As. Then hit Save. And next I'm going to set up my units. So I'm going to go to my Units menu. I'm going to pick my length as feet. The length here also covers your depth from your measured depth, and the example surveys that we're going to use are in feet. And then I'm also going to pick the units for my magnetometers and my accelerometers. So for our magnetometers, we have the following options. And then for our accelerometers, we have the choice of G or milli-G. And we also have the option of inverting our Z-axis for our accelerometers. So if I toggle this on, you can see that this is active. What this does is it flips the way that the Z-axis is pointing. So when it's off, the z-axis is pointing down towards the bit, and when it's on, it's pointing back up towards surface. For our example, I believe we want it turned off. Don't worry too much if you don't know exactly what your units are. Once we've pulled in some surveys, I'll show you how we can use a bit of trial and error to work out which one is the unit that we need. Next, we're going to set up our QC limits for our raw surveys. So to do that, we go to our options menu and we go down to raw survey QC limits. Now, this is currently grayed out because in order to access it, I have to have my survey selection in my surveys tab set to raw surveys. So if I set it to raw surveys, go back to my options menu, it's now accessible. If I click on it, it'll open up the QC limits window. So in a moment, I'm going to enter in my reference values for my field strength and my dip, which I've taken from my geomagnetics model, such as HDGM or BGGM. And then in the QC limits window, I'm going to set my dip tolerance and my field strength tolerance. These values set how far the field strength and dip calculated from my surveys can stray from the reference values and are therefore considered outside of tolerance. So for default values, the dip calculated by my surveys can go 0.5 degrees above or below the reference dip before they're considered outside of tolerance, and likewise the field strength calculated by my surveys can go 0.3 above or below the reference field strength before it's considered outside of tolerance. Inside the QC limits window, we can also set a reference gravity field in G, and then we can set a tolerance above or below that reference gravity field, which our surveys are not allowed to fall outside of. If you have not been given a reference gravity field for your well, it's usually safe just to leave it as the default of 1. So once we start entering surveys, you'll see that for some of them, the dip and the field strength and the gravity field will be highlighted in red. This is to indicate that those surveys have fallen outside of tolerance. And then lastly, on the right hand side, we can set some separate QC limits for surveys that have been corrected using multi-station analysis. That isn't relevant for us, so we'll leave them for now. I'm going to leave my QC limits just as the defaults, then hit OK. So now we can start entering in our reference field magnetics. So in order to perform a short collar correction, you're going to need a reference field strength, a reference dip, a reference declination, and your grid convergence. And you also want to set if your north reference is grid or true. The total applied correction will get calculated automatically from your grid convergence and your declination. The latitude and the inclination to use values are not used in the short collar correction. Be aware that your reference field strength is always in the units of microteslas. So make sure that you enter this value here in microteslas and not nanoteslas, or you're going to get some pretty weird results. So I'll now enter my reference values for this example. So now I can start entering in my surveys. In order to perform short collar correction, we have to be in the raw surveys table in our survey selection dropdown. And we're going to need our surveys in the form of a measured depth and then the raw accelerometer and magnetometer readings. In engineering, the accelerometer readings are known as GX, GY, and GZ, and the magnetometer readings are known as HX, HY, and HZ. Other companies give these different names, so sometimes you'll see the accelerometers as AX, AY, and AZ, and the magnetometers as MX, MY, and MZ. The first line in my table is my tie-on line, and in the raw surveys table, this is the only line where you can just set your measured depth, your inclination, your azimuth, and also your TVD, north, south, east, west, and vertical section values. So I'm going to leave my tie-on at surface, and then for my first survey, I'm going to click on Insert After. This will insert a new line, and then I can start entering my values. So I could start entering my values manually, but given that raw surveys are usually to 4 or 5 decimal places, this could be very tedious and prone to error. Fortunately, engineering is copy and paste compatible, so if I have my surveys in a table format, such as this Excel spreadsheet that I have here, what I can do is I'll highlight my first survey, copy it, and then I can go back into engineering, just right-click on the leftmost cell and click paste, and that will paste in my survey. So now that we've got a survey in the table, we can take a look at our table columns. Once we've entered our measured depth and our raw accelerometer and magnetometer readings, everything else is calculated automatically. In the inclination and azimuth columns, we have our raw inclination and our raw azimuth with no correction applied. And then over here, we have our HL, GT, and dip columns. And these are showing our raw field strength, gravity field strength, and dip calculated from our accelerometer and our magnetometer readings. And you can see that the field strength and the dip are highlighted in red, and this is because they are falling outside of our tolerance limits that we set in our raw survey QC limits. And then to the left of these columns, you've got the azimuth short collar corrected column, the field strength short collar corrected column, and the dip short collar corrected column. So these are your azimuth, field strength, and dip after the short collar correction calculation has been applied. So you can see that there's been a slight correction made to your raw azimuth. And you can also see that the correction has pulled the field strength and the dip back inside our tolerance window. And then on the right here, you've got the high side tool face, and you've got the delta azimuth column. So this is the difference between your corrected azimuth value and your uncorrected azimuth value. And then to the right, it's calculated our TVD and our local displacements north-south, east-west, and in the vertical section. And you can set your vertical section azimuth up here in the top left in the vertical section section. And then further to the right, it is just calculated the tool face, the dog leg, your build rate, your turn rate, and the course length. So now we're going to enter in the rest of our surveys. What I could do is I could just highlight this whole table, copy it, and then just paste it into our raw survey table. But instead, I'm going to show you the other way of pulling surveys into our table, and that is using the import survey function, which you can find by going to File and Import Survey. And this will let you import your surveys into your table from a file, and it can be from various file formats. So we've got tab delimited text files, space delimited text files, comma delimited .csv files. You've got Excel tables, navigator short color correction text files, and then you've got LAS files. So if you've received some surveys from the field in the form of a LAS file, you can import those all in one go using this import survey function. So I have a LAS file ready. You need to select the LAS file format so that it appears, and then you just select it and hit open. And this will open up the import survey dialog. So we can see the contents of our LAS file here, and we've got our surveys down towards the bottom. We need to set the start row for our surveys. So for this example, that is row 87, and then the end row is row 192. And then below that, we need to set which of the columns in the LAS file represent the columns in our table. So to do that, you just go to the drop-down box at the top of each column, and you can choose between your measured depth, your GX, GY, GZ, HX, HY, HZ, and then you've got N/A if you don't want to import that column in. The default setup for my columns is correct, so I don't need to change anything, but if you did, you would just go through each column, choose the correct one from the drop-down box, and then for any that you don't need, so all these over here to the right, you just select N/A. And once you're happy, you hit Import. You'll get a warning saying that this will overwrite everything that is already in your raw surveys table. So I just go to hit OK, and that will pull in all of the surveys in the last file. This has removed my tie-in line at the top, so if you want to enter it back in, all you need to do is select your top line and hit the Insert Before button. So I'll add a line at the top, and then I can set my tie-in line back to surface. There we go. I said before that if you don't know exactly what your accelerometer and magnetometer units are, it's not necessarily a big problem because we can use a bit of trial and error to work out what they should be. If your units are wrong, then you'll see that your raw field strength, gravity field strength, and dip will be completely out. And if you have another source to compare your raw azimuths against, you'll see that they also don't match up. So, as an example for my accelerometers, my correct unit is G, but if I change it to milli-G, you'll see that my gravity field strength goes from close to 1 to 0.001, which is a very long way out. So that's an indicator that my units for my accelerometers are incorrect. And likewise, if I change my magnetometer units to something that's incorrect, you'll see that my field strength is now miles away from my reference field strength, and so is my dip. You can see my reference dip is 67, but it goes down to like 10 down here. And often this is so far out that the short collar correction can't bring these back inside to tolerance. So what you want to do is just experiment with your units until you find the one that gives you raw readings which are closest to your reference. So now that I've got all of my data entered into my table, first thing I'm going to do is save my project, and now we can take a look at our results. So you can see for most of the surveys, the raw field strength and the raw dip were outside of our tolerance window, but the program has applied the short collar correction, and you can see that for most of them, it has pulled the field strength and the dip back inside our tolerance. You can see in the azimuth short collar corrected column, we have our azimuth results with the correction applied. However, for a couple of our surveys, the correction has not been enough to pull these surveys back inside the tolerance window for our field strength and our dip. And also for a couple of them, the surveys fell outside of the tolerance window for our gravity field strength as well. So your company will have its own policy on surveys outside of tolerance, but for me, I would consider these surveys as failed, so I want to delete them from my survey table. And to do that, I'm just going to select each row by clicking on the row number, and then I'm just going to go down and select delete. It'll ask if I want to delete the selected rows. I say yes, and I do the same for this one, which has got the failed gravity field, and then this one, which is the second one with the failed field strength and dip. And that should mean that all of my corrected surveys are now inside my tolerance window. And I will save one more time. And now I want to output my results as a report. Like I said before, the tables in Innova Engineering are copy and paste compatible, so you can select any part of the table that you want, right click and go to copy, and then you can paste it into another file format that works as a table, such as Excel. Also, if I click in the top left square up here in my table, it'll select my entire table. Right click and go to copy, and then I can go into a program such as Excel. Just click paste, and that will paste my entire table into Excel, which I can then print or email as I wish. The other way I can output my results is by going up to File and going to Print Reports. And this will bring up my Generate Reports dialog. In the Charts and Reports training video, I go into detail in how the Generate Reports dialog works, so I'm not going to repeat it here. Instead, I'm going to show you where our survey results are so that you can select them for your report and print them out. So you want to go to the Surveys tab, and then the selection that you want here is just the raw surveys. So I'm going to select just raw surveys. I'll set my report format as Excel, and then I'm just going to click Print. And that will print off my short color correction results as an Excel table. And that concludes the short color correction training. So we'll now move on to the magnetic interference calculator. This is the magnetic interference calculator results window. What the magnetic interference calculator does is that it takes a BHA that you've entered and a set of surveys, and it estimates whether or not you have enough non-magnetic material around your survey sensor to get accurate magnetometer readings without requiring any correction, or if the steel components in your BHA are causing too much interference and are pulling your magnetometers outside of their tolerance window. And then you can use those results to decide whether or not short color correction is going to be sufficient for this BHA, or if you need to use some other type of correction, such as multi-station analysis, or if you need to go back to the drawing board and add some more non-magnetic material to your BHA. In order to get to this point, we need to enter some data into our drawstring section of our drawstring weld geometry and fluids tab, and we need to enter some survey information into our surveys tab. The other tabs are not required for the magnetic interference calculator. So I'm going to start with a new project. So I'm going to go to File and New. I'm going to give my project a name. And then I'm going to go to File, Save As, and save it on my computer. As always, we start with setting our units. So we go to the Units menu, and the units that we're concerned about are our length. This covers both the measure depth of our surveys, but also the length of the components in our BHA. We need to know the diameter of our components. And if we are using raw surveys for our surveys, we're going to need to know the units for our magnetometers and our accelerometers. We also need to set our QC limits, and remember that we can only access our QC limits window when we're looking at raw surveys in the Survey tab. So I'm going to go to my Surveys tab, change my survey selection to raw surveys, and then I can go up to Options and open my QC limits dialog. And for the purpose of this example, I'm just going to leave my QC limits as the default. And now I can start entering data, and I'll start with my drill string. In the hydraulics training video, I go into much more detail on the mechanics of constructing a drill string in the drill string tab. I'm not going to run through them here. I'm just going to import in an example BHA so that I can show you which inputs into the drill string are important for the magnetic interference calculator. So to import my BHA, I'm just going to go to File and Import BHA, and I will find my BHA file that I exported earlier. So I just select it and then hit Open, and this will import in my BHA. For the purposes of the magnetic interference calculator, you need to know your component type and component OD. This is because the calculator uses these two bits of information to calculate the pole strength of your components. You also need to know the length of all your components, and in the non-magnetic column, you need to check in the checkbox which of these components are non-magnetic. You don't need to enter any other information into the drill string for the purposes of the magnetic interference, so I have not entered any information into the component details for any of these components. You don't need an ID, you don't need a weight. Technically, you don't even need a description, but it's useful to put one in just to avoid confusion. You also only need to go up from your bit up to the first piece of steel after your non-mag material. So in this BHA, I can actually get rid of this crossover and this drill pipe. One last thing to point out is that for stabilizers, the OD that you enter into the OD column is the OD of the body, not the OD of the fins. And that's all the information that you need to enter into the drill string. The other parts of the drill string tab, so the wheel geometry and the fluid properties, are not important for the calculator, so you can just leave them blank. And then we can move on to our surveys. Just like with the short color correction, we need to enter in our geomagnetic reference data into our field reference, our dip reference, our declination, and our grid convergence. But we also need to add in two extra pieces of information. This is the latitude in decimal degrees format, and we also need to enter in our survey offset. So this is the distance between the end of the bit and our survey sensor. So I will now enter in the data that I've got for this example. And don't forget to change your grid reference to true if your surveys are referenced to true north. So now that I've entered this information, I can start entering my surveys. Unlike with short color correction, the magnetic interference calculator does not have to use raw surveys. You can use actual surveys or well-planned surveys. Whichever survey you have selected from the survey selection drop-down box when you run the calculation is the surveys that will be used. So for this example, I have a set of interpolated surveys from a well plan, which I will just copy in from Excel. So I have my surveys in an Excel document. I'm just going to select them all, right click and copy, and then click in the top left cell, right click and hit paste, and that will paste in all my surveys. So I'll just save, and now I'm ready to run the calculation. So to do so, you just need to go up to your Calculate menu and select Well Path Magnetic Interference. This will run the calculation and bring up the Magnetic Interference Calculator results window. If you close this window and you want to get it back without running the calculation again, you can go to Survey Correction Results and then select Well Path Magnetics. On the left-hand side of the results window, we can see the configuration for our BHA. Then displayed next to it, we can see our reference, field strength and dip. We've also got our sensor offset. And then we've got these L values and P values. So the L values are just lengths that are used as part of the calculation. The first one, L1, is the distance from the bottom of the bit up until your first piece of non-magnetic material. And then L2 is the distance between that point and your sensor. And then L3 is the distance between your sensor and the top of your non-mag material. And the p-values, P1 and P2, are the pole strengths of the components that are touching your non-mag material. So the value P1 is the pole strength of the stabilizer with a body OD of 4 3/4 inches that is below our non-mag material. And then the value P2 is the pole strength of the 4 3/4 inch drill collar that is above our non-mag material. And the units for these pole strengths is milliwebers. Depending on how you set up your BHA, there are 4 possible configurations, and these can have more than 3 L values and more than 2 P values. So the standard configuration, and the one that we're using in our example, is no intermediate steel, So that is just one continuous length of non-magnetic material in your BHA. You can also have intermediate steel above. So you've got a piece of steel in between your non-magnetic material and it's above your sensor in the BHA. You can have intermediate steel below, which is the same thing, but your steel components in between your non-mag material is below your sensor. And then you can have intermediate steel above and below, which is a combination of the previous two configurations. You've got a piece of steel above your sensor and a piece of steel below your sensor, sandwiched in between your non-mag material. If you're not happy with your pole strengths that you've been assigned here, you can manually set them yourself, and you can do this by clicking on the Override Pole checkbox down the bottom. This will let you enter in your own custom pole strength for any steel components that are being used in the calculation. Just remember that if you change any of the values here, or if you turn off Override Pole strengths again, then you need to click on the Recalculate button to rerun the interference calculation. So now we can take a look at the results table itself. The first three columns are your measure depth, inclination, azimuth, and these are just the surveys that you entered into your survey tab. The azimuths in the results window are always to magnetic north, so they will look different to the azimuths that you entered into your survey tab because those are referenced to either grid north or true north. The calculator takes your surveys and it takes the geomagnetic reference data that you entered into the survey tab and it calculates a theoretical BZ value for each survey. This is the expected magnetic field strength in just the Z-axis if there was no interference at all from any steel components. And then the program will estimate the errors in your results due to the presence of steel components in your BHA. So delta BZ gives you the estimated error in your BZ value. Delta azimuth gives you the estimated error in your azimuth result. And then delta dip gives you the estimated error in your dip. And then delta HL does the same thing but for your field strength. And then we interpret these results by looking at the delta azimuth, delta dip, and delta HL columns. If the error in the dip and the HL are greater than the tolerances that we set in our QC limits window, then they'll be highlighted red. If a large number of the dip and HL values in your results window are highlighted in red, then that's a clear indicator that you do not have enough magnetic spacing in your BHA. If all of your dip and HL values are within tolerance, that's not enough to say that you do have enough magnetic spacing in your BHA. You would then go and take a look at your delta azimuth column, and you would see if the estimated errors in your azimuth are acceptable. What an acceptable error in your azimuth is will depend on your company policy, but here at Innova we use a general industry standard of about 0.5. That's the maximum acceptable error in your azimuth when taking surveys. So you can see here that all of these surveys have a much greater error than 0.5. So it's pretty clear from these results that there's not enough magnetic spacing in this BHA. On the right, we have this SCC delta azimuth. So the program also attempts to predict the error in your azimuth after short collar correction has been applied. And it's this column that is affected by the latitude value that you entered into your survey tab. And you can see from these results that short collar correction will have quite a large effect on the azimuth error. Most of these are below or around 0.5, so I might consider running this BHA but making sure that I correct my azimuths with short collar correction. If these errors were still too high, I would have to consider another form of correction such as multi-station analysis or going back and adding more non-mag material to my BHA. And the last thing that we can do is to export out our results. So we can do that by going up to File in the top left-hand corner of the results window and selecting Export. It'll ask you to save your file and you have a choice of file types. You can save your results as a text file or you can save your results as an Excel file. If you save it as an Excel file, it'll include a diagram of your BHA configuration. So we'll save it as an Excel file. And now we have our results exported into Excel. That concludes the magnetic interference calculator training video. We'll now move on to the question and answer section. After each question, try pausing the video and see if you can answer the question yourself before seeing the answer. So question 1, what are the units for the field reference strength, also known as HLREF, in the survey tab? And the answer is the field reference strength is always in microteslas. So if you get your field reference given to you in nanoteslas, remember to divide that number by 1000 before you enter it into the survey tab. Next question. Other than setting your units, which other step is important during setup for short color correction and magnetic interference? And the answer is setting up your raw survey QC limits in the options menu. Remember, you can only access the raw survey QC limits when you have raw survey selected in your surveys tab. Question 3. What component information is required when building the BHA for the magnetic interference calculation? And the answer is you need your component type, your component OD, your component length, and then whether or not that component is non-magnetic or not. Next question. What extra information in the survey tab is required for the magnetic interference calculator but not for short color correction? And the answer is, on top of the information that you need for the short color correction, you also need your latitude and your survey offset. And then lastly, where should I check if I can't remember what a function in short color correction or magnetic interference calculator does? And the answer is, the best place to look is in the help file. Look in the options menu, the calculate menu, the dual string and the surveys tabs. And also don't forget that you have references for your pole strengths and your short color correction limits in the appendices. That concludes the question and answer section. So now we'll move on to the exercise. When performing this exercise, you should start with a blank project, but you're going to need survey and BHA input data, as well as some geomagnetic data. So you should copy this data from one or more of the example projects. Start with a short color correction first, set up your units and your raw survey QC limits, and then take the reference field strength, dip, declination, and grid convergence from one of the other examples. Copy in some raw surveys from one of the examples that has some raw surveys available, so either the short color correction example itself or one of the complete examples. Try experimenting with units to see how they change the gravity field strength, magnetic field strength, and dip results. If there are any bad surveys that have failed in the magnetic field strength or are still outside of tolerance after being corrected by the short color correction, then delete those rows from your survey table and then use the report generator to print your results to Excel or PDF. Once you've done that, you can move on to the magnetic interference. So you can use those same raw surveys that you use for short color correction if you want to, or you can take a new set from another example. Add the latitude and the survey offsets in the surveys tab, and then copy or import a BHA from another example. Run the calculator and see what results you get. And then close down the calculator and try going back to the BHA and adding some non-magnetic components, and then rerun the calculation and see if you now have enough non-magnetic material in your BHA that the calculator predicts that you don't need to perform any other correction on your BHA. Then you can export your results from the calculator window into Excel. If at any point you become stuck, refer back to the video for a refresher. Thanks for watching. If you need to get in contact with us, you can do so via the two email addresses displayed here.